What's going on, guys? Johnny Bannon here with Trepa Technologies. In today's video, we're going to be going over domain 2.2 switching technologies in the Network Plus N10-009 exam. If you like this content, please like and subscribe, share it with your friends, ring that bell, and let's go ahead and jump right into it. So I'm going to get my face out of the way here. We don't need my face there for learning, guys. So here's our objective. So it's actually pretty... Well, this could take me, I could take maybe 6 to 8 hours to explain all this, but I'm not going to. This is the Network Plus exam. But we're going to talk about VLANs, what a virtual local area network is, what it does for us. We're going to talk about the VLAN database and how it's just something we need to be aware of where our VLANs are stored. It may not always be in a startup config NVRAM that we typically see in our Cisco devices. Go over SVIs, go over different things we can configure on a switch interface. And then this second to last one here, spanning tree. It's so sad. I usually have to spend hours teaching this in my CCNP, CCNA classes, but we're going to just do an overview of it. It's going to hurt my heart. And then we'll talk about MTU sizes, okay? MTU is in the switching portion, even though we mostly see it being changed on the router when we do encapsulation, IPsec, stuff like that, but that's okay. All right, so jumping right into it. What is a VLAN? So a virtual local area network allows us to logically segment our traffic at layer 2. All we need to know, honestly, at the end of the day, what this does is inserts a 4-byte tag into the Ethernet frame that says, hey, you're a part of this VLAN, okay? So if you get assigned to gig 09, and on that switch, we put gig 09 into switch port access VLAN 10. When you send traffic to that switch is going to insert that 4-byte VLAN header, and that standard is called IEEE 802.1Q. And that's going to segment you throughout the network to say that this traffic, this data payload in this Ethernet frame is part of VLAN 10. So it's a logical subdivision of a physical network. It lets us isolate our traffic, lets us have multiple broadcast domains, because at layer 2, that's exactly what it does. However, VLANs are going to be part of their own broadcast domain. So a VLAN is also going to have its own subnet. So at the router or the routing device, we may have a sub interface that says, hey, encapsulation.1Q10 and then 192.168.10.1/27. So you're part of that broadcast network. And then we could have VLAN 20, a part of the next subnet in that range, right? So as you can see here, we have 4 different devices here, each in their own subnet. This design is wrong. I got to put that in different VLAN numbers. I'm going to pause this video real quick. There we go. Now it's fixed. You can see that these devices are in their own VLAN, and that VLAN is tied to its own subnet. Okay, now VLAN database. So a VLAN database is just saying that some switches, depending on the vendor, in Cisco, this is true of some switching iOSs. When we create our standard range of VLANs, the standard range is 1 through 1005. That's the number range. So VLANs 1 through 1005. Those VLANs get stored in a VLAN database, a separate file in our flash that's not part of the startup config. So the VLAN database stores all VLAN related information on a switch. Now, extended range VLANs are actually stored in the startup config. They want to just mention that in the Network Plus exam, so just give you the basics of that. Okay, so what is a switch virtual interface? So an SVI is when at our switch, our layer 2 device, we want to enable layer 3, so we want to enable IP addressing, and we want to assign an IP address to correlate to that VLAN, we create an SVI. So in this example, we have our access switches here that let's just say are layer 2 only. We got VLAN 10, VLAN 20 here. And where's our router? Well, our router is actually going to be this layer 3 device that says, hey, interface VLAN 10, digital switch 1, when you see tag traffic coming across your trunk with the VLAN 10, and then you inspect it, you say, okay, I have interface VLAN 10. I'm the default gateway. It's going to route traffic for you. So we create SVIs to give us that ability. So an SVI is used on layer 3 switches to allow inter-VLAN routing between VLANs. Okay, additional configuration. So the native VLAN. So the native VLAN, also known sometimes as the default VLAN, is just out of the box, our switch, right? That native VLAN is, or the default VLAN is 1, but what the native VLAN does, it's actually going to carry some some control plane traffic across our switches. So the native VLAN carries untagged traffic on a trunk link, so anything that's not part of a specific VLAN tag, right, is going to be part of the native VLAN. And by default, that native VLAN is 1. So since we know this, the best practice is always to change it because of something called VLAN hopping attacks, okay? Now, control plane traffic, so like Cisco Discovery Protocol, Link Layer Discovery Protocol, Virtual Trunking Protocol in Cisco, PAG-P in Cisco. The native VLAN carries that control plane traffic across switches, okay? So just a little tidbit there. The voice VLAN is another specific VLAN. So all VLANs, if I create VLAN 10 and I give it the administrative name of printers. So within our entire enterprise, we say VLAN 10 is for printers. So if I got to hook up a printer to the network, I put in a ticket, say, hey, I'm hooking up this printer. That goes to the NOC, the network team. They say, okay, tell me what port on the wall it is. Okay, we look at our diagrams. That's part of this patch panel going into this switch. Put that switch port in VLAN 10. That's for the printers. So we may call it a printer VLAN, but it's not. That VLAN 10 is just something we designated. We said, hey, VLAN 10 is for printers, but that's still an access VLAN, right? That's what we call that, an access VLAN. We can give different names to these access VLANs. A voice VLAN is something completely different. We're not just naming a VLAN voice administratively for our diagram, for our SOPs. A voice VLAN is something specific that we can set on an access port that says switch port voice VLAN, this number. And if someone's tagged with this VLAN number, we're going to give additional quality of service tags to it, like class of service, specific for voice, for VoIP traffic that needs lower latency and less jitter across that voice over IP network, right? So the voice VLAN is going to be something specific. 802.1q tagging. This is just a general term, right? It's the 802.1q, encapsulation 802.1q. When we insert a VLAN tag, it's using the IEEE 802.1q standard. Okay, link aggregation. So link aggregation is a technique that combines and bundles physical interfaces to create one logical interface to improve bandwidth. We call this port bundling. We call this ether channel in Cisco. We call this port channeling. We call it NIC teaming on servers. All have the same goal. Hey, on a server, I have a NIC that has I have a 4 NIC unit. So a NIC card that has 4 gigabit Ethernet. I connect that to my distro switch or the Cisco Nexus switch in my data center, whatever the case may be. And instead of only having traffic come across one port, I'm going to logically bundle those ports to make it seem like one logical interface and get that improved bandwidth, okay? So in Cisco, we have PAG-P and LACB configuration. When we actually create these port channels, you can see that down here. If you pay for our self-paced training, we'll actually go through how to configure LACP and PAG-P in a Cisco environment. So the link aggregation control protocol is multi-vendor, it's non-proprietary, and that's typically what we see a lot in multi-vendor situations. Okay, speed and duplex. So this is just going over at the interface level, we have speed. So the speed of a switch port refers to the rate at which data can be transmitted. We can set the speed. If it's gigabit Ethernet, it should be default at 1,000, right? But we could change that potentially. Duplex, we have half and full. So half duplex is send or receive. Full duplex is send and receive. We always want to be in full duplex, right? Full duplex is what we want. Sometimes we have errors. We have duplex mismatches where we are plugging in a PC to a switch, and for some reason or the other, the switch port or the computer is at half duplex. The switch is at full duplex. We're going to have errors there. We're going to have collisions. So we always want to be at full duplex where we send and receive. All right, so spanning tree protocol. So the spanning tree protocol, I guess this is another subject that we could take a couple hours going over. But to summarize it, it does exactly one thing, and that is prevents broadcast storms, prevents a switching loop from occurring. So what is a broadcast storm? What is a switching loop? Well, if we understand the fundamentals of how a switch forwards frames and forwards broadcast frames, we know that when a switch receives a broadcast frame, that's the destination MAC address is all Fs, the actual broadcast MAC address, it's going to send it out all active interfaces besides the one it came in on. And if you look at a design like this, where we have redundancy between these switches, let's say that's switch 2 over here on the bottom left, receives a broadcast frame of switch 1 and switch 2 over here, it's going to forward those out, the respective interfaces that it's supposed to, right? Every active interface besides the one it came in on. And then it's going to keep doing that forever and ever and ever. And then the MAC address table, or the content addressable memory table on that switch is going to become overloaded. it's going to throttle the CPU. And what I mean by that is the CPU is going to reach a threshold where it cannot operate normally anymore. So you may look at that design and say, okay, well, if we don't want a loop, let's take away that cable. Let's stop the loop. Let's just get rid of this cable here with my mouse is hovering over, and we don't need that redundancy. Well, then there's your problem. Where's our high availability? Well, what happens if we get rid of this physical interface? Like actually just pull the cable. We pull it out of there. And then this switch has an issue, and this port actually comes down. Well, now we cut off our users that are potentially connected to this switch to the rest of the network. So we still want redundancy, but we want a protocol that will automatically prevent those broadcast storms. So 3 simple steps, right? How does STP operate? So spanning tree operates by electing a root bridge. So that's going to be the king of the castle, so to speak. So the first step in preventing broadcast storms when using spanning tree is the switches are going to create BPDUs, Bridge Protocol Datagram Units. And in that BPDU, frame, packet, whatever, right? We're going to have a bridge ID. And the lowest bridge ID is going to automatically be the root bridge. Okay? After we select the root bridge, we're going to have to select the shortest path to the root bridge, okay? From each switch that's not the root bridge, non-root. And I keep saying bridge, okay? Something I tell my in-person students and my virtual students a lot. A switch the actual piece of hardware called a network switch came out after the spanning tree protocol, or there was a timeline I don't know the exact timeline, but essentially we used to call a switch a bridge, right? That's when we had hubs and we had a bridge. So then the bridge protocol datagram unit, that vernacular just kind of carried over into our switching vernacular when talking spanning tree protocol, okay? So I say root bridge, I say shortest path to the root bridge, 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 bridge. Really, you could say the root switch as well. And you may hear me say that interchangeably when I say elect the root bridge or elect the root switch. Okay, so anyways. So step 1 of the STP process, to get our network fully converged and to make sure that we have redundancy while not allowing broadcast storms. So step 1, elect the root bridge. Once all the switches have decided who the root bridge is, now every non-root switch, non-root bridge switch, has to say, what is my shortest path to that root bridge? So now I have to say, if I have a path, let's say I'm down here again, to switch 1, which is the root bridge, and I have this path that can also technically reach switch 1 over here, which is my shortest path, which has the lowest cost. And we're going to elect that by, again, the cost, okay? So whatever the lowest cost is, that's going to be your path to the root bridge. And we're going to call that a root port. And then now the topology has to decide, okay, every switch has its root port, the shortest path to the root bridge that we're going to forward traffic out of. But now, between switch 2, switch 3 here, which one's going to be blocking? Which port's actually going to be blocking to prevent that broadcast storm? And we're going to get into that, okay? There's 3 major types of spanning trees. So there's the original spanning tree, which is 802.1 delta, 802.1d, which takes about 30 to 50 seconds to converge, okay? You can see this chart down here at the port roles, port states, the differences between that original spanning tree and something called rapid spanning tree. That works the exact same way, but as the name suggests, it's a lot quicker. Its full convergence is, at the white paper, since I've learned networking, I've always been told 2 to 4 seconds, right? But it can be quicker. And then we have another version of spanning tree called multiple spanning tree that we're not going to get into, but it allows you to segment a big campus network in a way to have multiple instances of spanning tree for different VLANs. Now, for some of my Cisco guys who have done networking forever, you're going to tell me, isn't spanning tree always on a per VLAN instance? And you're right. Cisco switches do a per VLAN spanning tree, okay? But the actual IEEE standards, it's not a per VLAN thing. So 802.1 delta, 802. Whiskey, which is spanning tree and rapid spanning trees, IEEE, RFC standards, respectively, they don't talk per VLAN. But yes, spanning tree, if you're on a Cisco switch, can be on a per VLAN basis. Then multiple spanning tree protocol does it in the, it's part of the protocol to do it on a per VLAN basis. We're not going to get into this here, a little bit more advanced. Like if you're ever studying for Cisco, you don't learn about that till the professional level certs, the actual configuration, how you have a root instance. Anyways, we can get deep into that, but we're not going to, okay? Now, I'm going to pause the video real quick. I'm going to bring up my whiteboard, and we're going to dive into that spanning tree election process a little bit more, go over different tiebreakers, kind of go over that bridge ID, how we elect if every single switch has the same root, the bridge ID numbering system. So it's in increments of 4096. We're going to go over determining the shortest path and what happens if we have redundant links to the root bridge, which actual interface, if everything is equal, what's the tiebreaker, right? So let me pause the video and let me bring up the whiteboard. Okay, guys, so here we have a little topology here. So here's what we're looking at here. We got 3 switches. They're all connected with a redundant link between switch 2 and switch 3 here. I'm going to try to type out as much as I can. Let me expand this a little bit so we can see it better. The root states, or the port states and port roles. Okay. Now, let's check out this situation. We're going to do spanning tree like it's a per VLAN, okay? Because it's going to matter. So let's say we have VLAN 10 that's been propagated throughout this entire network. As in, we created VLAN 10 on these switches. We have users accessing VLAN 10, okay? So this is for VLAN. I've been getting some comments that my handwriting is horrible, so I'm going to slow it down. VLAN 10, okay? So, first step of spanning tree, we want to prevent broadcast storms here. First step is we have to elect a root bridge, okay? Now, as you see written up here, the root bridge is going to be the switch or the bridge with the lowest BID. That's the bridge ID, okay? BID is bridge ID. So the bridge ID is going to be a priority number, okay? So that's going to be 0 through 6, 1, and I'm going to pause the video so I can get this right. 61440, okay? That's our bridge ID range. And guess what? This is going to be in increments of 4096. So what does that mean? That means that if I want to hard set a bridge ID, like let's say I want to make switch 1 the lowest bridge ID no matter what, I can either do 0 or 4096 and then increments of 4096. So I can't set a bridge ID at like 20, okay? It's in increments of 4096. Okay, so what's the default? What's the default bridge ID? The default is going to be 32768. 32,768. That's the default. So let's say each switch here, I'm going to type now. Each switch's bridge ID is 32768. Okay? And I'm going to copy this and paste it at all these other switches. They're all 32768. Okay. So now, well, we still have to elect the root bridge. So now we get into our tiebreakers. So since we're doing this for VLAN 10, something that's also unique is that in that BPDU, that bridge protocol datagram unit, when we're looking at the bridge ID, we're actually going to add the VLAN number onto this bridge ID. So yes, you heard me correctly, spanning tree on a per VLAN basis, you're going to add that VLAN tag as part of the bridge ID. So if we were doing spanning tree, figuring out the root bridge for VLAN 20, on all these switches, they all had VLAN 20, it's been created, it's been propagated throughout the network, whatever, right? What would our bridge ID be then? It would be 20 plus the default, okay? Or 20 plus whatever the bridge ID is. So that'd be 32788. But in this case, we're figuring out for VLAN 10, okay, per VLAN spanning tree instances, that's what you're commonly going to see. So that's what we're going to go over here in this whiteboard session. So we still have the same problem though. They're all default. So what's the tiebreaker? And I'm going to zoom in here. The tiebreaker to elect the bridge, the root bridge, if all things are equal, the bridge IDs are equal, is going to be the lowest MAC address. So we take a look at switch 1, switch 2, and switch 3, which has the lowest MAC address. These are hexadecimal digits. The A equals 10, B equals 11, C equals 12. We're just converting it to like, what we look at as regular whole numbers. Switch 1 has the lowest MAC address. So guess what? Guess who is going to be the king of the castle here? Switch 1 is the root bridge. So switch 1 is the root bridge. Awesome. Now we could hard set that. We could go in as network administrators and engineers and say, hey, switch 1 is connected to the router up here, the core, distro, whatever the case may be, whatever your architecture has. And we could say, if it's Cisco from global config, spanning tree, VLAN 10, root, priority, 4096. And then we absolutely know, and we don't have to get into the tiebreakers. But okay, now that we've elected the root bridge, what's next? Now from switch 2 and switch 3, we have to determine the shortest path to the root bridge. So we have to elect a root port. Now from the root bridge, since we are the root bridge, this is going to get into the port roles and port states. When we're the root bridge, guess what, guys? Every single interface is going to be what's called a designated port. It's going to be designated and it's going to be forwarding, meaning that we're going to be able to receive and send traffic out all of our interfaces. So our port role is called designated, and we're going to be in a forwarding state. Okay? So the root bridge doesn't have a root port because we don't need to know the shortest path to the root bridge. We are the root bridge. Okay? So let's bring it all back. Spanning tree. We're preventing broadcast storms. So what spanning tree does automatically is going to send BPDUs. And these BPDU packets, along with the spanning tree protocol, is going to do three things. First, elect the root bridge. 2, once the root bridge is elected, the other switches are going to elect a root port and determine which interfaces are going to be discarding. And then we're fully converged, okay? So kind of 2 to 3 steps, all right? We're done with step 1. We already determined who the root bridge is based off the lowest bridge ID using the tiebreaker of this MAC address because all of our bridge IDs are at default. So now switch 1 is like, okay, well, if I'm the root bridge, that means every single one of my ports are going to be designated and forwarding. So pretty much after we elect the root bridge, now on a per switch basis, we have to elect our port states and port roles, okay? Okay, now let's check out switch 2 and switch 3. So to determine the shortest path, what's going to be our root port and forwarding towards the root bridge is going to be based off cost, okay? So we have 2 ways from the perspective of switch 2 to reach the root bridge. One out gig 00, which has a cost of 4. And lower cost is better, right? Lower cost is better. So this is a cost of 4. It's also a cost of 4 to go out gig 01. But then to reach the root bridge out gig 01, we then have to go up gig 00 out switch 3. So when we do that, if we want to forward out gig 01 of the root bridge, we come this way with a cost of 4, and then back out gig 00, which also has a cost of 4. So we have 2 ways we can do this. We can send traffic this way, and it'll cost us 4, or we can send traffic this way, it'll cost us 8. So guess what we're going to do? We're going to elect gig 00 as the root port. So gig 00, and I'm going to erase this, right? Gig 00 is the lowest cost. So that's easy for us. We know that gig 00 is going to be our root port, and it's going to be forwarding. Okay? So the role is root. It's a root port. And our state's going to be forwarding. And this is the same for spanning tree and rapid spanning tree. We're going to put the same thing over here. Switch 3, same thing, right, guys? Okay, but now we have an issue. Now, let's bring it all together. We establish our root ports. But what's the whole point of spanning tree? Prevent broadcast storms. So now, let's take a look. Well, between switch 2 and switch 3, this cost is the same. Okay, so if the cost is the same when electing a discarding port, we move on to something called the interface number. So between switch 2 and switch 3, they're both gig 01. So that's also equal. So now we're going to go based off the MAC address, which has the lowest MAC address. Really, what we mean by this is, okay, which has the better bridge ID, right? Between switch 2 and switch 3, everything is equal. It's cost of 4. These interfaces are equal. So, which has the lowest bridge ID? It's going to be switch 2, okay? So what we're going to do here is say, hey, switch 3, I have a higher bridge ID, and our cost is the same. So what's going to happen is gig 01 here is going to be designated and forwarding. And let's just say we're doing rapid spanning tree, which is probably what we're going to do here, right? In our modern networks, is switch 3 is going to be in a alternate, if we're doing rapid spanning tree, and a discarding state. Alternate role, discarding state. And what we're saying here is that if gig 01 comes down here, this is going to turn into forwarding and designated, okay? And that's how we elect it. Now, before we move on, you may say, okay, I get that. That was pretty easy. Well, let's say this was fast Ethernet over here. Let's say this was fast Ethernet 01 and this was gig 01. Well, that cost would be 19, right? So then this would flip. Since it's a lower cost, this would be a discarding port, okay? Now let's look at another scenario. What if, okay, we got something like this. We have switch 1 here. Its bridge ID is 4096. And we have switch 2 over here. It is 8192 for the bridge ID. So guess what? This is the root bridge. And let's say this is gig 0/1. This is gig 0/2. This is gig 0/1. And this is gig 0/2. Well, we know the root bridge. Our interfaces are going to all be designated, right? We don't have to worry about that. But switch 2, it has a problem. Out of these two, which one is it going to elect as the root port and which one's going to be discarding? It's going to be based off the lowest interface, okay? So since gig 01 is a lower interface number, this is going to be our root port. And this is going to be our alternate port if we're in rapid spanning tree, and it's going to be discarding, okay? Now then, of course, obviously, let's say this is an F, then it's going to flip, right? Because it's cost. But the cost is the same, right? So that's how we determine it, okay? Now, what same thing here. Like, let's say this is gig 0/2. Oops, I kind of made a bad line there. Let's say this is gig 02 and this is gig 02. So now we're in another kind of pickle here. And essentially the same thing is going to happen is since switch 2 here has the lowest bridge ID, this is still going to be, right, in our designated forwarding state. But then switch 3 here has to determine which one's discarding. Technically, gig 01 is better, okay, than gig 02 here. But you're like, this can't be in a designated state in this alternate or blocking, right? So what would happen here? Well, in this scenario, what spanning tree is going to do, it's going to say, okay, well, look, I have the lowest bridge ID, switch 2 here, and switch 3. But we have a dilemma because we have two ports connected to each other, and we're going to need 2 discarding ports now, okay? Since switch 3 has the higher bridge ID, which means it's worse, they're both going to be alternate, okay? They're both going to be alternate to prevent that loop. Okay, so that is spanning tree. Now, let's get back to the slides. Go ahead and finish this up and then do our questions. Okay, I think this is the last slide. So last thing we're going to go over is MTU. Again, this is just talking about the maximum transmission unit of an Ethernet frame or packet is 1500 bytes. That's the regular size. If it's less than 64 bytes, I think it's called a runt. If it's higher than 1500 bytes, up to 9000, we call that a jumbo frame. And if we want to change the size of our MTU, our default MTU, we can do it at the interface level. All right, now let's go and do our quiz. All right, guys, so now we're at our learning management system here. Let's go ahead and do our quiz for domain 2.2.2, which is our switching, right? So we can come here into our lessons, domain 2.2.1. We can scroll down here, and let's go ahead and take our domain quiz. Let me zoom in on this here. Okay, so question 1. What is the purpose of 802.1q tagging in VLANs? So we're going to go with D here, to allow multiple VLANs to communicate over a trunk link. If you want to see the explanation, we can do that here. Question 2. What is the primary function of a switch virtual interface? We're going to go with B, to route traffic between different VLANs. Question 3. What is the main benefit of configuring a voice VLAN? It's going to allow our voice traffic to be assigned a higher priority. It's like QoS, right? At the layer 2, at the switching level. Question 4. Which of the following is true about VLANs? We're going to go with A here. VLANs segment a local area network by adding or inserting a 4-byte header into the Ethernet frame. That's the 802.1q standard 4-byte header that says your VLAN number. It does local segmentation at layer 2. Question 5. Which protocol is used to prevent loops in a switch network? Gotta go with spanning tree, right? Question 6. What is the default maximum transmission unit for Ethernet networks? That's going to be 1500 bytes. That's our default. And look at that. We got 100%. So I want to thank you all for viewing. Make sure you hit like and subscribe. If you're interested in getting access to this LMS, please hit us up. Look at the links in the bio, or excuse me, in the description below. And we'll see you in our next video going over wireless.